Hey everybody, this is Samaksh Goyal here,
And Sidhika?
and we're going to be talking about our 236 final project. Our project is titled Take a Seat on a Generated Sofa. So, if you're sitting on a couch, a sofa, a chair, a desk, a table, all this geometry and world around you can be represented in some format. In Blender, Maya, or other 3D animation tools, all this is represented as meshes. You can look at the faces, vertices, and edges, and look at the connection between them to understand how the world is represented. In the world of self-driving and autonomous cars, the world around us is modeled as 3D point clouds. 3D point clouds allow for an efficient and compact representation of the world around us. This is because for each object, all you need to know is a scattering of points on the surface of the object, and thus you only need to know the number of points, n, and three positions, x, y, and z, for all the points on your surface, and you can have your object. Uh, recent generative models have been made to be able to sample or create point clouds from a latent space. And our project is going to use different types of generative models to try to model and obtain these point clouds.
So as Avi mentioned, we're going to be creating different GAN and flow-based networks for point cloud generation. Specifically, we're creating 3 different GAN models, the RGAN, the LGAN, and the Wasserstein GAN, and one math-based flow model. I'm going to start by describing the difference between the RGAN and the LGAN models. The RGAN and the LGAN differ in what they treat as the data distribution. The RGAN treats the raw point cloud data itself as a data distribution. So this is the distribution of all possible lists of XYZ coordinates. The LGAN, on the other hand, treats the data distribution to be a latent representation, or all possible latent representations of the point cloud. These latent representations are obtained using the PointNet model's encoder network. PointNet is an autoencoder model, so I'll start by just giving a brief description on what an autoencoder is. An autoencoder is made up of 2 networks, an encoder network and a decoder network. The encoder network takes the point cloud and compresses it into a latent representation Z, and the decoder will reform the point cloud from this latent representation. Now, as opposed to just any old autoencoder, PointNet is special because of the permutation invariance properties of point clouds. What permutation invariance means is that when you have a point cloud, you can reorder the points within this point cloud and still obtain the same object and the same exact point cloud itself. So what that means when we're working with autoencoders or generative models is that no matter what ordering of the input point cloud is given to the model, it should always represent this latent representation of the point cloud the same way. So PointNet is different from other autoencoders because it uses 2 different, or tries to enforce 2 different properties in order to maintain this permutation invariance guarantee. So first of all, PointNet transforms the point clouds into an input and permutation invariant input representation before it runs the encoder network. This permutation invariant input representation is obtained using a symmetric function. Symmetric function is a permutation invariant function, and specifically what we do is we apply the symmetric max function on our input point cloud and use the output of this max function as the permutation invariant input representation. Now, second of all, we also obtain permutation invariance by using a permutation invariant loss function. Now, MSE or other standard loss functions are not permutation invariant, so instead we use the chamfer distance loss function. What the chamfer distance is it's a metric that compares 2 different sets of points. So in our case, we're going to be comparing the initial point cloud to the reconstructed point cloud. That's the output of the decoder network. Specifically, what the chamfer distance calculates is the distance between each point in the input point cloud. And we take each point and we find the closest point in the output point cloud, calculate the distance between these 2 points. And then we're going to take the average of all of these distances over all of the points in the input point cloud. That's this first term in the loss function. The second term is the same, just in reverse. So we take all of the points in the output point cloud, find the closest point in the input, and take the average. So this is the description of how the permutation invariance works in the PointNet autoencoder. And as a recap, this is what we use to get our latent representations for the LGAN. So now that we've described the difference between the RGAN and the LGAN, the third GAN model that we use is called the Wasserstein GAN. The Wasserstein GAN uses the LGAN's model construction. The only difference is that now, instead of using a standard GAN loss, we're using the Wasserstein loss. So the benefit of the Wasserstein loss is that it makes the training much more stable and allows us to get better results ideally.
Our last generative model is a flow-based model. Particularly, it's a masked autoregressive flow-based model. And what this means is that we will take as input a latent z and take as input mu's and alphas that have been created by passing the output data distribution x's through a series of neural networks to get our mu's and alphas that we combine with the z's to pass through an invertible function to get the next x's. This is typical of a flow-based model. And what this means is that we get slow sampling because we need to sequentially go from z1 all the way up to, or x1 all the way up to xn, but it allows for fast parallel training. The difference between our math model and that what we learned in lecture is that our math model uses the latent space, the 128 long vector that you get out of the autoencoder, as the data distribution. So instead of the x's being the 2048 by 3 point clouds, we instead use the latent distribution as our x's. Now let's take a look at some of the results we get from our models. In the top left, we have the R GAN, which is the raw GAN, which we see can't actually deduce any semblance of a couch. The points are scattered everywhere, and there's clusters, but we can't really see what they mean. However, on the right, we have the L GAN, which is actually able to construct reasonably looking sofas. And in fact, the sofa on the top left flourishes out, has the arm rests flourish out. If you look on the bottom left, we have our latent math network, or flow-based network. And we see this is able to learn a series of different sofa configurations, such as short and long sofas, and different kinds of L-shaped sofas, which we see on the left and the right in the math-based model. Now, what we take this to mean is that our generative model is able to learn and create a variety of different sofas that can be present in our space. Lastly, we have our Wasserstein latent GAN, which is on the right. We notice that this is not able to accurately produce sofas. Instead, just produces globs that kind of look like sofas, and believe the problem with this is just due to our hyperparameters. If we increase the strength of our lambda and increase and change the norm from an L2 loss to an L1 loss, it's possible this could produce better results.
We've just described qualitatively how our models do. Quantitatively, we're measuring the performance of our generative models using the chamfer distance metric. This is the same metric we use as the loss function for our autoencoder network. The chamfer distance measures the similarity between two sets of points. In our case, we're going to be measuring a set of points generated from our generative models and a set of points which is a sample from the data distribution. Here in this plot, we're mapping the distribution of the average chamfer distance. So what we're doing is we're taking 100 generated samples and 100 samples from the data distribution. We're measuring the chamfer distance between each generated sample and each real sample, and we're calculating the average across all of the different generated samples. We plot 3 different distributions for each of our generated models, so LGAN, Wasserstein LGAN, and LMAF. You can see that they all do very similarly in terms of the chamfer distance. Now our last distribution, which is shown in red, is for the data distribution. And what we're doing here is we're calculating the average chamfer distance between 2 sets of distinct samples from the data distribution. And we do this to show an ideal of how well our model could do if we were able to exactly replicate the data distribution. You can see that this chamfer distance distribution is skewed right. Now what this means is that for some certain examples, we have very high chamfer distance, and this means that the data distribution has a lot of variety. So for example, if we're comparing an L-shaped sofa to a rectangular sofa, we would get a very large chamfer distance. And what this says is that the chamfer distance might not be the best metric to be using to compare different samples. Overall, what we can see is that the LGAN does the best at modeling this skew distribution, and therefore we might say that the LGAN performs.
Cool, let's go over some conclusions and directions for future work. So the most important thing that we learned is that point clouds themselves are too rich, complex, and inconsistently sampled to develop systematic algorithms with. What this means is that we can't handle the point clouds directly as they are. Instead, we need to get some uniform, normalized representation of them so that we can use them with any ML algorithms. The way that we were able to do this was using the autoencoder. And we saw that the effectiveness of this by looking at the visualizations of the latent GAN and the latent math models, which produced reasonable looking couches. Another way that we could improve our current model is by comparing the distributions of the data and the generated models directly. Instead, what we use right now is a chamfer distance, which takes the distributions, samples from them, and then compares the data, creates a statistic based on the samples of these data sets, instead of looking at the distributions themselves. Lastly, a simple extension of this is to change a problem from a uniclass to a multi-class problem. What that means is that you go from a latent variable to a set of categories, say sofas, rockets, and cars. And then from these categories, you go more broadly to the set of point clouds associated with each of these categories. This concludes our project. Thank you for listening.